Good afternoon and welcome to the 7th in our 2021 webinar series delivered by Dr. Tim Sandle. These monthly webinars are covering different aspects of Annex 1. Hopefully they will help you prepare for when it goes live. Today's topic will cover water systems, microbial monitoring and qualification strategy. But before we start, just a few housekeeping tips. If you've got any technical issues, if you want to send a short message in the questions box on the right-hand side of your screen, we will attempt to try and sort the issues out for you. And during the webinar, if you would like to ask any questions, you can use the same questions box in the right-hand side. At the end of the webinar, time permitting, we'll try to answer as many of these as possible, and any we don't get round to, we will answer offline and share with you, along with a copy of the slides from today. So, welcome to Rssl's webinar series. Those of you that haven't met me before online, I'm Annette Russell and I'm the Sterile Manufacturing Lead at Rssl. I work in the commercial team here and I work directly with our pharmaceutical microbiology team to support our clients who are involved in both sterile and non-sterile manufacture. For those who've attended previous webinars, welcome back, and I hope you're enjoying the series so far. So Rssl can support you in many aspects of your manufacturing process. And if you want any further information about this after the webinar, please contact me direct using the details you can see on your screen now. This session, I've been introducing you to various members of our pharmaceutical microbiology team. And this month, it's Danny Laker's turn. Danny is a senior technician in the pharmaceutical microbiology group. He works alongside Aaron, who you may have met last month, in our cultures lab. And he has moved across from the water testing group and now is mainly responsible for running microbial identifications on our moldy top and media quality control. Hi, Danny.
Hello, Annette.
Hi.
Hello, everyone.
As before, can I ask you to give us a brief overview of what your role in the team at Rssl is?
I am a senior technician in the pharmaceutical microbiology department here at Rssl, and my main role centers around routine analysis in the cultures laboratory. I am mainly responsible for performing quality control checks on media to judge them fit for purpose and identifications on our moldy top system.
Okay, excellent. And this is a difficult question for most of you when I ask it, but what does a normal week look like for you at Rssl?
So for me, a normal week would start with Monday, where I would prepare reagents that I'm going to be using for analysis for the week upcoming, and I'll be reading and recording test results. On Tuesday, will be a better day to perform quality control checks on media. And Wednesday, Thursday and Friday, I'll perform identifications on the Molotov system. And it's pretty routine.
Excellent. As I mentioned at the start, you used to work in our water testing team, and today's webinar's been around water. I thought I'd ask you, what are the main challenges with water testing from your point of view?
So water testing is a pretty simple test. I think the main challenges are to ensure that all samples are as if they were freshly sourced. We try to test them as soon as possible, which I believe is a main challenge. And it can be a main challenge, especially if samples arrive, say, on a Friday. We try to get them on test as soon as possible so that we would test them on the same day. But other than that, it's a pretty simple test.
Okay, excellent. And finally, what do you do for downtime when you're not involved with helping clients with their microbiological requests?
So I'm a keen and avid footballer myself, and I enjoy going to the gym. However, this past year, I've recently got into playing video games with my friends, and that seems a little bit sad. But especially as people weren't allowed to leave their house for the best part of a couple of years, I found that was a pretty good way to relax in the evenings.
It's certainly a virtual world we lived in for a while back then.
Yes.
Thanks a lot, Danny. Thanks for giving us an overview of what you get up to.
No worries at all. Thank you.
So, as I've mentioned, here at RSSL, we work with a lot of our clients doing both their bulk water and purified water testing to Pharmacopoeia. And whilst you are familiar with our microbiology team based in the Reading site, 6 miles down the road at our main site, we can also offer a range of chemistry testing. We have 2 total organic carbon instruments, which can enable us to meet the fast turnaround requirements. And as you've heard, the microbiology team have the capability to test within 24 hours of sample receipt. We can also provide on-site training for you and help with the sampling process if required. And RSSL's training group can provide either bespoke training, or you can attend one of our courses, such as the Water Systems and Microbiological Control training course that is due to run. And if you're interested in that, if you want to contact me after the webinar, our training team will offer you a 10% off of the price for attending the webinar. Many of you will have seen this slide before. It's an overview of the services that RSSL can offer to help you with Annex 1. They're very varied and they cut across very many different laboratories. If you're interested in any aspects of Annex 1 support, please feel free to contact me and we can help wherever possible. So that's enough of me now. I'd like to introduce you to our guest speaker, Dr. Tim Sandle. I'm sure many of you will have heard of Tim and will subscribe to his many publications. Tim has over 25 years of experience in microbiological research and biopharmaceutical processing. He is a member of several editorial boards and has written over 600 book chapters, peer-reviewed papers and technical articles relating to microbiology. Tim has worked for a pharmaceutical manufacturer in the UK and also finds time to be a visiting tutor at both the University of Manchester and UCL. Hi, Tim.
Thank you very much for the introduction. Okay. So, welcome to the webinar and wherever you are in the world. Over the next sort of 40 minutes or so, we're going to have a look at pharmaceutical water systems, and we're going to be having a look at some of the risks of microbiological contamination, biofilms, some of the good design issues, some of the measures that can be taken to address contamination, monitoring and trending, and kind of recapping on some of the key learning points. So to begin with, we'll have a look at the different types of water that are found in pharmaceutical facilities. So we begin with potable water, or what's sometimes called mains water or towns water. And this is certainly within the UK would be the drinking water supply, but in other parts of the world it might be water that's drawn from a well of some description. And the water company, if there's a water company in place, will guarantee a certain level of testing. But if it's water in another part of the world drawn from a different source, then we should have an understanding of the level of pathogens such as E. coli and Pseudomonas aeruginosa as indicators of, say, fecal contamination and other organisms of concern. Wherever the water is drawn from, then the standard test is the heterotrophic plate count, and a limit of no more than 500 colony-forming units per milliliter would be applied to this starting water. And it's not atypical for the levels of microorganisms in supply water to change according to seasonality, because there's going to be variable populations based on the available nutrients, temperature, and the overall standards of the supply water. Then we have purified water. And this is water intended for the use in the formulation of medicines that are not intended to be sterile or apyrogenic. So purified water can be used for oral and topical products, and in granulation processes for tablets and capsules. And also it's the feed water for the production of water for injection and for pharmaceutical grade clean steam. And purified water can also be used for the initial rinsing of equipment and preparing of cleaning solutions. So there's a requirement here, according to Pharmacopoeia, of no more than 100 colony forming units per milliliter, or if we're testing a 100 ml sample by membrane filtration, which is often the preferred method, then that would be no more than 10,000 organisms per 100 milliliters of water. And then the third type of water is water for injection. So this is the highest quality of water used in the pharmaceutical industry. And traditionally, this is always prepared by distillation, but this has now been supplemented by reverse osmosis in the last few years following change to European Pharmacopoeia, although there are some additional concerns around reverse osmosis, particularly in relation to endotoxin control, which we'll have a look at in a few minutes. So WFI is used for the preparation of injectable medicines, for dialysis, irrigation solutions, turning into steam for autoclaves and so on. And the Pharmacopoeia requirements are no more than 10 colony forming units per 100 ml. So by specifying per 100 ml, that makes the membrane filtration method mandatory. And also there needs to be a low level of endotoxin, which is defined as less than 0.25 endotoxin units per milliliter. And this is where water for injections gets its name. So it's of water of a standard that could be injected into the bloodstream and not cause a pyrogenic reaction. Now there's different methods of producing water. So I mentioned reverse osmosis. So this is the primary method for producing purified water, and it can be a method for producing WFI. So reverse osmosis units are semi-permeable membranes, and by virtue of there being a substantial pressure differential, this drives water through the membrane. So we achieve the required not only microbial and endotoxin quality, but also a chemical quality. And this is where the term purified water comes from, because it's a reference to its chemical properties in terms of the trace levels, organic carbon and conductivity. And often these systems exist in a series, so there might be water might pass through one RO unit and then a second RO unit and so on. And we're really creating this kind of molecular sieve-like approach. And our removal of contaminants and the like comes about through size exclusion. So we can separate out ions, salts, microorganisms, and so on. Then in relation to the next type of water, we have distillation. Sorry, just wait for this slide to move. There we go. So distillation functions by turning water from a liquid into a vapor, and then from a vapor back into a liquid. And the endotoxin, which is the key thing at this point we're interested in removing, is removed through this rapid boiling process, which causes the water molecules to evaporate, and the relatively larger fragments of endotoxin, which are lipopolysaccharide molecules, perhaps sometimes bound with other impurities, to remain behind. So the design of a distillation unit to produce WFI is to achieve 2.5 to 3 log reduction in endotoxin through the distillation process. So it's good practice in order to show that the distillation unit is functioning as designed, to verify what the endotoxin challenge is in the supply water, and then to check the endotoxin levels coming from the still. So probably put a limit of no more than 250 endotoxin units per mil for the supply water in order to achieve that 3 log reduction to show water of less than 0.25 coming from the other part. So the core objectives with water purification, just to summarise, is to reduce the levels of chemical components in the water, and this is to prevent interactions that might occur with drug substances or the formation of materials that might be toxic to the patient, to reduce the microbial bioburden to our required level, and also have a system of control to prevent the proliferation of microorganisms should they get into the water system, and then also to remove endotoxin, and then by virtue of the control of the microorganisms to also prevent their generation through the proliferation of organisms. So water systems, particularly purified and mains water systems, will contain a level of microorganisms, but what's of concern are the numbers and frequency of those organisms. And with non-sterile pharmaceuticals, we have particular concern about the presence of unwanted organisms, which can sometimes be under this umbrella term of objectionable organisms, and two examples are the Burkholdia sapacea and Pseudomonas aeruginosa. And here contaminated water presents a concern because water is both a growth vehicle for many of these aquatic organisms, which can survive under these low nutritive conditions, but also it can be quite an effective vector for spreading contamination once it's released into the production area through aerosols. So just moving on now to biofilms. So we've got a great picture on the slide there of a biofilm formation in a pipe. So a biofilm comprises of any group of microorganisms in which the cells are bound to each other and they're bound to a surface. And the fundamental concern is with water systems. And as these microorganisms adhere to the surface, then they start to produce extracellular polymers, and these facilitate the adhesion. And they also give the biofilm a structural matrix. And often the term biofilm community is used, and the reason for that is that the it's been demonstrated through a number of means now that the organisms within the biofilm community have different methods of communication. Goes under the banner of quorum sensing, so they can sense aspects to the environment or to the structure and signal and undergo, can sometimes trigger different kind of physicochemical properties. The adherence of the biofilm is also a combination of various attractive and repulsive forces. And the primary weak point, as we'll look at it in a little bit, is with poorly designed pipes, particularly where the water flow goes down. And then the main challenge that is presented to contaminated water systems is where the organisms are slowly released. So we get this pattern of free-floating cells that are released in clumps. So the trouble is the kind of pattern that would be developed with where a biofilm is present is that sometimes you'd see counts, sometimes you wouldn't, but the period where you're not seeing any counts doesn't mean the biofilm's gone away. It's just the way of that biofilm cycling through its community. And that's partly bound up in this mechanism of biofilm formation, which is shown on the slide. So we get the basis of this formation of the slime-like material, which is largely polysaccharide based and undergoes the technical term of a glycolax. And this provides a degree of protection because these extra polymeric substances to a degree give a resistance to chemical disinfection, and a degree they give a resistance to heat as well. And the biofilm attachment happens relatively slowly, but once it becomes advanced, then it becomes very, very difficult to remove. So we go through this phase of reversible attachment, which is the slow part of the phase, to irreversible attachment, which is the part when the community is more mature and it becomes more difficult to remove. Gram-negative bacteria tend to form biofilms more readily, and this is obviously a concern to water systems, and that's partly due to their cell appendages and also to do with the lipopolysaccharide, which is the endotoxin causing substance as well. Another important factor is surface charge as well. And it's kind of an irony as well, is that many stages of the water purification process can also create conditions which can promote biofilm formation, because we're purifying the water and we're creating niches of low nutrient richness. Those organisms that can survive then tend to become the hardest organisms, which are then those that are most predisposed to trigger off a biofilm formation. Okay, so now we'll have a look at some of the aspects of water system design. So we've spoken about contamination risks leading up to the biofilm. So how do we design good water systems and maintain them? Well, there's a very kind of generalized outline of a pharmaceutical water system on the slide, designed to generate water of high purity. And it will have these various functions. So it'll have a break tank, an activated carbon bed, a water softening column, deionisation columns or devices, and then a reverse osmosis system, which might lead to a distillation system depending upon the design. And then there will be a tank to hold and store the water, and then there will be some form of distribution system through a network of pipes leading down to user outlets or plumb directly into different pieces of equipment. And the overriding aspect of design, which is of concern to us in this webinar, is with having measures in place designed to minimize microbial contamination. So what we're going to do now is just run through some of those elements of the water system and look at particularly where contamination might pose a concern to us. So the break tank is important because its function is to prevent water that might be contaminated during production from re-entering the supply water and promoting colonizable niches of contamination. And the concern is always going to be with the incoming mains water, because there's an ability for those organisms to form sedimentation and to attach some size to the sides and bottom of the tank. So regular maintenance, cleaning and disinfection of the break tank is important in order just to kind of reduce that tendency for biofilms to develop. Next we have carbon beds. So these are large surface areas of finely divided charcoal. And these are highly efficient at removing low molecular weight organic materials and also any oxidizing additives in the water, so particularly chlorine. So they're very important for the commencement of making the water chemically pure. But it is important that these are sanitized regularly, that the beds are treated with hot water or steam to keep contamination low, and then there will need to be a fairly regular frequency of replacement, because they'll reach a point when those methods are no longer effective at destroying the microorganisms that might be present. And then we have water softeners, and these are required in most areas, particularly where the water is hard, and this is necessary to remove the cations in the water, the divalent cations like calcium and magnesium, before they can interfere with the function of the deionizers in the next step. And the process works by ion exchange, so we're replacing the calcium and magnesium with sodium ions. And again, the concern is that the resin matrix, a bit like the activated carbon beds, gives an enormous area for potential microbial colonisation. So we need to have sanitisation methods in place, such as UV light or even the addition of chemical to maintain the quality of the water at that point. And then we have deionisation, and this is where the technology can vary because there are different technologies available for deionisation. So there can be deionisation columns, electrodeionisation, electrodialysis, and so on, all with the same objective and generally involving charged resin columns. And an advantage here is that the regeneration process often uses chemicals which are themselves biocidal. So it could be 1 molar hydrochloric acid or 1 molar sodium hydroxide. But columns that remain unsanitized for long periods or which are not regenerated on a regular basis then again pose a colonizable niche. And experience generally shows that if contamination is going to form, then it's more likely in this location and more likely if we're not regenerating every couple of days. So if we're leaving it too long between regenerations, then that's where the contamination risk arises. Then it's important to have smooth internal surfaces inside tanks and pipework. And this is necessary because microorganisms adhere less well to smooth surfaces than to rough surfaces. So often we will be specifying a surface roughness value, which is the RA measure. And there's a cutoff of about 0.8 microns. So above 0.8 micron surface roughness, microbial attachment is easy. And below 0.8, then microbial attachment becomes more difficult. But we also need to have good design practices for things like pipe joints and welds, because these can sometimes disrupt the smoothness. It's also important to have continuous movement of water. So turbulent movement within the tank and rapid flow through pipework. And here we'd use the Reynolds number to express the degree of turbulent flow through pipework. And we want to be ideally targeting something like 3,000 or more. And this is because where we have strong shear forces, then microorganisms will adhere poorly to surfaces, but where that force slows down or disappears, then it's quite easy for microorganisms to adhere to surfaces and establish biofilms. So often a biofilm formation in pipework is normally the consequence of a blockage or a slowdown in the water rate, or due to a poor design such as dead legs, where water can stagnate in branch pipes, particularly when something branches off from the circulating main and causes water to slow down. It's also, we need to have good design principles with the water storage tanks as well. And we should have an understanding of their capacity, rate of use, frequency of flushing and sanitization. And an ideal water system turns over at a regular basis to prevent contamination buildup. Where we get slow turnover, then we have greater potential for contamination. So it's important in things like if there's a facility, a short-term facility shutdown, that the water continues to turn over. So it might appear wasteful in terms of running taps for no apparent purpose, but it is important to help contamination control. It's also important to prevent microbial contamination from the outside air. So we obviously need to vent tanks, but these should be fitted with appropriate filters to stop contamination ingress. In terms of circulating water, another important concept is that the ring main should be sloped, or it means having a drop from the point of origin to the point of return, so that we have drainability. And also good engineering practices would require that leaks are addressed. So although there may be a leak and there may be a pressure differential, particularly when there's fluids involved, then it is quite, it's not too difficult for contamination to ingress into the water system, particularly for motile bacteria. Further good design point is with hot water systems, and having hot water systems achieves far better control than cold water systems, because the water is maintained under conditions of high temperature for both storage and distribution. And the kind of temperatures that start to give effective control tends to be around from 65 degrees Celsius. Some facilities run 70, some run at 80, but there aren't many gram negatives that will survive beyond 65. But then for health and safety reasons, we need to have a cooling system that allows water to be cooled down through heat exchangers so that it's of a suitable temperature for personnel to use that water. It's important that heat exchangers are also well maintained, because if they're not, then they can be a source of contamination. With cold water systems, these are at greater risk because they're running at the temperature which many aquatic bacteria actually like. So they can provide an ideal matrix for colonization if they're not controlled well. So we need to make sure that we've got good pressure differentials and there's frequent sanitization in place, and we have good water flow. So we don't want to avoid colonizable surfaces. And generally it's ozone or hydrogen peroxide, which is used as the fairly frequent decontamination chemical. So just in summary for this part on the design of water systems, we want to have well-designed pipes, smooth internal surfaces, fast-flowing turbulent water, continuous movement of water where we can, and also to be conscious that towards the end of water delivery to the user, then if water remains stagnant in valves around water points, then or they're not in frequent use, then this can be a point of contamination. I'll just go on and say a little bit more about water points. So the point of delivery is often where contamination will occur. So the water system is well maintained. It's often where the user uses the water. So the first thing is the transfer piping or tubing. So that should be made of a non-toxic material, because we don't want to go to the trouble of purifying water and then adding toxins, leachables from the tubing that might then enter the product again. But in terms of microbial controls, then it's important that the transfer tubing is drained after use and is hung up, so disattached from the outlet. It should be changed regularly using tubing that has undergone some form of sanitization, like autoclaving. When using the tubing, it needs to be care taken to avoid splashback from sinks, where we could recontaminate the end of the tubing with aerosols. And also we want to flush that tubing before use. But it's important that whenever the microbiological test samples are taken, that they're taken exactly the same way that the process area would use the tubing. So if the process area flushes for 30 seconds, you don't want the microbiology department flushing for 1 minute, because the water they'll be testing would be unrepresentative of the water that's used in the process. So despite all these good design practices and control measures, then contamination does occur with water systems, and I've experienced some horror stories with contaminated water systems. So there are options available when these events occur for treating and improving water quality. And the use of the method partly depends upon what the root cause is of the microbial contamination, the source of the problem, and also what kind of quality of water we're using and what our desired microbial control level is. But there is the use of chemicals such as chlorine, or with ozone and hydrogen peroxide, as we mentioned. And here there's an effectivity, but there's also a concern with damage to the stainless steels. There's good flushing techniques, we mentioned, particularly at user outlets. There's the application of heat and holding water at high temperatures. There are some options for filtration, but these tend to get frowned upon because they're normally indicative of poor practices if there was ever a need to filter water at point of use. So with chemical treatments, so does tend to be this division into the chlorine-based ones, so sodium hypochlorite, chloramine, chlorine dioxide, and then the peroxygens like hydrogen peroxide and peracetic acid on the other side. And the important point here is the concentration of the chemical and ensuring that the chemical is left in place for a suitable contact time, and also balancing that off with the risk of corrosion that could occur. And the concentration of chemical depends upon the length of the water system and the flow rate. But for example, if we're seeking to chlorinate, for example, then we start to get effective levels of active chlorine at around 0.2 milligrams per litre of free chlorine, using a contact time of 30 to 60 minutes. So that's kind of what we need to be targeting. And also we need to be sure we can get the chemical out of the system as well once the process is finished. So there's always going to be a degree of flushing involved as well. With purified water systems, then ozonation tends to be the most common method, normally then using ultraviolet radiation to break up the ozone to make it suitable again after the ozonation process has happened. To a degree, UV light can disinfect, but getting the contact time sufficient can be challenging. With temperature, then again, the temperature of 65 degrees and above is very effective, although some choose to run at higher temperatures. But the idea is that the water is continuously circulating at high temperature, therefore it is continuously self-sanitizing. And generally, heat is the most effective control method for keeping contamination in check. Obviously, once a biofilm forms, then it can often be a combination of heat and chemical methods. But in order to maintain control without the presence of a biofilm, then heat is effective because very few organisms that could ever be found in water could survive at those temperatures. But if a serious contamination event is suspected, then the ability to superheat as well is often built into hot water systems. So this could be taking the temperature up, almost like turning it into a continuous autoclave type system to 115 or 121 degrees Celsius, which is often a technique to tackle biofilms, sometimes in conjunction with chemical treatment as well. But we can only achieve this level of temperature control with a hot water system and one that's made out of stainless steel. So if we've got a cold water plastic system, then the reliance is very much just on chemical treatment. Just a little bit more about outlet controls as well. So as I said earlier, this is kind of the main point of contamination if the water system is well designed. And it is important that we're using the right kinds of tubing. So I mentioned about toxicity earlier, but it also stands that some components promote microbial adhesion more than others. So synthetic rubber-based components are more likely to become contaminated than hoses made from other materials as well. So there's quite a lot of choice to be made around this part of the process, the degree of flushing, the type of tubing, how we control that tubing, and so on. The kind of worst case but ultimate control measure, if there is an extensive biofilm, is to remove sections of the pipework completely. And this is obviously very time consuming because it stops the production process and takes a long time to do and can be very costly. So that degree of extreme biofouling is very, very challenging indeed, and nobody really wants to be in that situation. It's also important in terms of good practice as well, if we're rinsing when we're cleaning equipment, is to ensure that we have effective cleaning validation. And part of the effective cleaning validation, we are segregating clean equipment from dirty equipment and avoiding the aerosols from dirty equipment, recontaminating clean equipment. So that kind of goes off down a cleaning validation route, but it's just another important control measure to consider. Okay, so let's move on to microbial sampling. So it's important that samples for microbial analysis are taken properly and that good aseptic practices are used. So samples have been taken as production would use it, but in an aseptic manner. And also that we have some degree of qualification around the hold time. So it will be typical, and it's actually drawn from UK drinking water testing standards, is that samples are tested within 2 hours or they're held at 2 to 8 degrees for no more than 24 hours. And it can be prudent to qualify that process of that part of the laboratory testing so that we're avoiding either organisms growing too fast or organisms dying off, so we're getting a representative sample. In terms of microbial testing methods, then within Europe, the monographs for WFI and purified water require that R2A agar is used, so that's Rssl's second generation agar. And this is a medium that is specially formulated for recovering of organisms from nutritively depleted environments, such as a water system. In the USP, the choice of agar is left to the user to use. And there's a choice of method, so purified water can be tested by pore plate or membrane filtration. Membrane filtration is the superior method, and membrane filtration is required for WFI. And obviously, if we're doing things like diluting water, then we need to make sure that we're still able to produce a population count that's within the limit of the water itself. And there are some rapid microbiological methods emerging on the market, which we haven't got time to go into, but there's counting organisms in distribution systems by using types of flow cytometry, or there's fluorescent labeling techniques as laboratory methods as well. It's also really important that the results from water systems are trended, and this is something that anyone who's heard me speak before will say, you know, there's no point carrying out microbiological testing if you're not going to look and trend the data. And this is particularly so for water systems where there's going to be day by day, week by week, month by month variation. And also we need to trend so we can try and predict in advance whether an outlet needs quarantining or we need to undertake a sanitization of a water system. But also we get an understanding of how a water system behaves, say, during times of high and low usage. For early part of water generation, we can look more for seasonal validation, seasonal variations, and it can also help us to predict the time between water sanitizations, for example. So we've got an example here of a control chart that's looking at a water system over the course of a year. So we can use some of this data to maybe even help set alert levels, and also to look at how the water is behaving. So in this particular case, if this was ideal, that this particular company would have taken action, maybe, or at least start being concerned around 0.57 on the chart. These are actual weeks, so rather than letting the water system drift so far out of control, but it's just showing some of the things that can be derived from trend charts in terms of trying to predict when things are going wrong. Another advantage of trend charts, as shown on the slide there, is a much bigger look. So that's a 2-year trend chart. And there is, on this particular one, a degree of seasonality. So there are peaks in the summer period. So this could relate to water generation, and it might alert to when the higher levels of bioburden are found, and perhaps some additional controls might be required. So, in terms of bringing this webinar to the end before we go on to Q&A, we've kind of looked at some of the risks around pharmaceutical water distribution systems and touched upon, the primary risk is microbial adhesion. And this also goes back to something I think I said when we were looking at disinfectants, is that microorganisms, if they have a choice, prefer being on surfaces rather than being in a free-floating or planktonic state. So wherever there's an opportunity to gravitate to a surface, microorganisms will always seek to do so. And where this adhesion builds up, then there is a risk of initiating biofilm formation. And if we get biofilm formation in a water system, then it exacerbates the contamination risk, and that can lead to anything from things like slowly introducing contamination. But it can also increase the corrosion rate of pipes, and can also then lead in for non-sterile pharmaceuticals to a predominance of pathogens of concern. So we looked at Pseudomonas aeruginosa and the Burkholderia cepacia complex. And this also means that microbial control to a degree is a matter of concern, not just for microbiologists, but also for engineers and the users of the water, the production personnel. So ideally, if we're building a new water system from scratch, we'd put in all of those quality by design elements to design, control, and generate the water system. But if we're inheriting a water system, then we need to make sure we've got enough monitoring and trending to understand how the system performs, and to then have a degree of control within the water system for when things go wrong. And I think, just to recap something else I said, where it's often the slowing down of water which presents the one of the biggest problems. So where we've got a slowdown of the turbulent flow of water, we've got non-ideal joints or welds or sloping pipework with too much of a drop down, then these are all the kind of factors that can allow organisms to attach, and we develop these kind of niches of concern and so on. Okay, so that's the main part of the webinar over, to give a flavour of these design and control and testing factors, and I'll hand you back over to Annette for Q&A.
Thanks, Tim. So I've got some questions. I did have some issues seeing some of the questions come through, but I've got some come through now. So I will ask the ones that I can see, and any that I can't get around to, as I mentioned at the start, we will answer offline. So I've got a question from somebody, Jane, who said, how can endotoxin enter a water system?
So the one experience I had with endotoxin in a water system was a repair to a water system where a valve needed replacing. So it was some engineering work that was done, and the standard protocol was that after the work had been done, that part of the subloop was supposed to be flushed to drain. So you'd kind of reduce any contamination present by flushing with copious amounts of the clean water. But on this occasion, it was reconnected and wasn't flushed, so contamination had entered, and that then led to endotoxin being released from organisms that then contaminated the valve. A second example was again relating to a repair, but it was also during a shutdown, and it was a hot water system. But this particular subloop, the appropriate valve wasn't turned, and that part of the water subloop remained at ambient temperature and gave an opportunity for microbial growth, and again the release of endotoxin. So these were both WFI systems, but they're both post-distillation. So the stills were working fine. It was events subsequent to that led to these contamination events.
Okay, right. I have a question from Christopher who says, so how do we ensure that we have good flow of water to minimize biofilm formation without causing turbulence, which can cause biofilm formation?
The import, well, it's odd actually. It can also, it's often sometimes water that's too laminar as well can also pose quite a risk. So the key thing is measuring the flow rate, and there's a dimensionless measure of that, which is the Reynolds scale, and it's about the pace of flow and the level of forces that are in operation. And there's different scales of that, but a lot of research has shown that a Reynolds number of 3,000 or more, whether that water is turbulent or laminar, is sufficient to keep the organisms in suspension and to create sufficient force to stop them adhering. Then the slower that number becomes, then the easier it is for organisms to attach as they touch pipework.
Okay, and I have a question about the R2A. Somebody says, can we replace the R2A with TSA if we have a study to prove that TSA can recover environmentally stressed organisms? And that's from Zeba.
Okay. Well, the first point is that if you're going to replace R2A with TSA, then you're using a different method to what the pharmacopoeia is instructing. So it is possible, of course, to do variations from the pharmacopoeia and to show validation data. So yeah, anything is possible through that route, but that would require a license change and a discussion with the regulator. The thing is that obviously R2A has been especially formulated, so it's been with us since 1985. So it's the work done by Rssl and Geldrich, and it is a medium that is supposed to be better for recovering organisms from water. So you're going from organisms that are living in a low nutrient environment, and they go onto this agar that only contains the bare essentials for growth, and that in theory, if those organisms go onto a highly nutritious agar like TSA, then they may not be recoverable. So I don't know the particular study that's been done, but it's important to have ensured that the environmental organisms that have been used in that study have been subjected to the same stresses that organisms in water would have been done. So, you know, it might be holding those environmental isolates in distilled water for 7 days, for example, and then using those organisms to do the challenge. If you were just using healthy laboratory cultures to do the challenge, then those results may not quite be representative of recovering from the water system. So I don't know the in and out study, but it's just be careful with that. Another important thing is that sometimes people find it hard to recover organisms from the R2A to then take for identification. And again, that can be because of the transfer from R2A straight onto TSA. So there is an intermediate agar called R3A, and this has it kind of in between R2A and TSA. So it contains more nutrients, but not enough that it becomes a shock to the organism. So I always kind of think about it as somebody who's got on a really strict diet. Then you want to gradually reintroduce them to food, which would be the R3A, rather than feed them, make them eat 30 donuts or something, and they get the sugar rush and then keel over. So it's that kind of a concept.
Okay, I like the analogy there. And I've got a last question really from Helen. How often should we sample a water system?
Again, the USP chapter for water gives a lot more guidance on this. Under the European Pharmacopoeia, it's very much left to the users to decide, and also depends upon the grade of water. But if you're running a WFI system and you're in the business of making sterile medicines, so you take the highest requirements, then you need to be doing, in my mind, supplies and return every day, source tank every day, and then at least a series of representative water outlets every day, and then maybe complete the entire cycle of water points within, say, a 7-day period. For purified water and for non-sterile manufacturing, then you can kind of more expand that, say, over a month or something. So I think with a lot of things, the frequency is determined a little bit by the criticality of the activity and the importance of the data, and making sure there's regular data coming in every day, and also with the degree of control that you have. So a risk-based approach would be the answer, and I'd kind of go with those frequencies personally, but your risk-based approach might produce something else.
Okay, thanks. So just a very quick question from Roger, because it's connected. He says, can you confirm if the sample should be taken from hoses attached to the outlets or not?
The answer to that one is they should always be taken as the production staff would use it. So if the production staff take it with tubing, then take it with tubing. If the production staff don't take it with tubing, because I've been stung in an FDA inspection before when it started off being the same way. Production changed their practices, didn't tell the QC microbiologist, and ended up doing taking water in slightly different ways, and that related to tubing, non-tubing, and also with the flush time as well. So just make sure it's the same. That's the key message.
Excellent. Okay. Well, thank you, Tim. Thank you for that informative webinar on water. Thank you out there for attending. I hope you found it useful, and we appreciate the questions you have asked. I'm sorry I couldn't get all of them on around to ask Tim, but as I mentioned, I'll forward them on to Tim, and I will share them with you along with the slides from today and a link to the recording so that you can watch again if you want to. Just a reminder that our next webinar in this series will be on the 24th of November, and that will be sterility assurance in cell therapy products. And don't forget, if you're interested in RSSL's training course on water systems and microbiological control, please do contact me for that 10% discount, and I can put you in contact with our training team. For now, on behalf of RSSL, the sterile manufacturing team, I'd like to thank Tim for continuing to deliver such informative webinars for us, and for all you out there listening today. please don't hesitate to contact me if you have any questions or if you need any support with any projects. Have a good day.